So let's look at the statement from the textbook that the percent ionization decreases as the concentration increases. So let's look at the problem that we ended with in class, where we have a 0.1 molar solution of acetic acid, and that has a Ka of 1.7 times 10 to the minus 5. We can solve for our equilibrium concentrations of conjugate base and H3O plus using our equilibrium constant expression and assuming that X is small in relation to the initial concentration of acid, 0.1 molar. So what we find is that when we solve for X, we get a concentration of 1.3 times 10 to the minus 3 molar. And that's our concentration of A minus and our H3O plus concentration. So from that, because it's our H3O plus concentration, we can take minus the log and find the pH and get 2.89. And we can also find the percent ionization, where this is the concentration of A minus at equilibrium over the initial concentration of weak acid. So 1.3 times 10 to the minus 3 divided by 0.1 times 100 to get the percent, we get 1.3%. So let's see then what happens if we increase the concentration of the acetic acid to 0.5 molar. So our ICE table is going to be very similar. 0.5 initial concentration of weak acid, 0 moles per liter and 0 moles per liter of A minus and H3O plus. We're going to have minus X moles per liter of HA, plus X and plus X for A minus and H3O plus. So at equilibrium, we'll have 0.5 moles per liter minus X for HA concentration, and X moles per liter of both A minus and H3O plus. So our Ka, we can plug everything into our equilibrium constant expression, 1.7 times 10 to the minus 5 equals X squared over 0.5 minus X. Now in the last problem, we were able to make the assumption that X was small in relation to 0.1, and that was a valid assumption. And so increasing the concentration of HA is not going to invalidate that, so it's actually going to make it more valid. In any case, we can assume that X is small compared to 0.5. And when we multiply both sides of this equation by 0.5, we will get 8.5 times 10 to the minus 6 equals X squared. Take the square root of both sides, and we will get X is equal to 2.92. We can, oops, that's a 9. 2.92 times 10 to the minus 3. And that's our H plus concentration, which means we have a pH of 2.54. And we can calculate the percent ionization here as well. So we're going to take the 2.92 times 10 to the minus 3 divided by 0.5, and we will get, times 100, and we will get 0.58%. So you can see that the percent ionization has decreased, so we can do a little comparison here. For our 0.1 molar HA acetic acid versus our 0.5 molar acetic acid, percent ionization for the 0.1 molar was 1.3%, and for the 0.5 molar it's gone down to 0.58%. The concentration of H plus has gone up in the higher concentration solutions. We go from 1.3 times 10 to the minus 3 molar to 2.92 times 10 to the minus 3 molar. And then the pH is also lower in the higher concentration solution. And these two things are what we would expect. I think the percent ionization would be the one thing that's a little bit surprising, that it decreases, but we're still producing greater amount of products than with an increased concentration of reactant, just as we would expect with Le Chatelier's principle. But the relationship is based on our Ka, and so it's not a linear relationship, and so that's why our percent ionization isn't as great for the